updating my little task list of shit I need to do for the projects. No. It was just so fast. That's why the load.
Hi, Shalane. We can hear you now.
Oh yeah. So
okay, I'm gonna have Dr. Rickles is going to announce you, and then you can share your screen and begin. I'm gonna shut my sharing off so that you can transfer to yours.
sounds good.
Hello?
Yes, we can hear you, Dr. Rickles. We can hear you, so you can announce when you are ready. We will take questions after the seminar, so you can either announce your questions in the chat or raise your hand or ask after we're done.
Yeah, hello. This is Jim Rickles. I'm the director of the NEES facility. I want to welcome everyone, all the participants, and particularly the speaker, Dr. Shailene Pei. Let me first say a little bit of background about the seminar series and then the speaker himself. The LEHIGH seminar series is organized by our NEES experimental facility. We have on average one a month. It's to basically try to convey to the community, the research community practitioners, some of the latest research and some of the transformations that will take place in earthquake engineering and natural hazards. The other thing that we want to do as well is to market our facility in terms of providing you with information about how you may be able to utilize some of the NEES facilities for some transformative research. So having stated that, our speaker today is Professor Shailene Pei. He's from the University of Colorado School of Mines. His presentation is entitled Brief History of Wood Seismic Research from Light Frame Wood Systems to Mass Timber. I should mention that his research is very diverse and focuses on natural hazard mitigation through performance-based engineering, numerical modeling of structural dynamic behavior, traditional innovative timber systems, and large-scale dynamic testing. And he'll be mentioning several things in his presentation, but I think one of them will be one of the projects he's currently leading, which is sponsored by the National Science Foundation, and it's funding 6 universities on a collaborative effort related towards seismic design methodology for resilient, tall, cross-laminated timber buildings. And I want to add to the fact that Dr. Pei is currently the chair of the ASC Wood Technical Administrative Committee, overseeing 4 wood engineering related committees. So with that, I think I'll go ahead and extend the welcome again to Professor Pei and hand it over to you, Shailene.
Yeah, thanks, Jim. I hope everybody got a good Thanksgiving break. Then back to here at School Mines with almost finals week. So anyway, it's thanks for the opportunity to talk on the LEHIGH seminar series. Today what I'm gonna do is I'm just gonna go through what I kind of provide one of my perspective on wood research on seismic, specifically probably more in the US. So basically, let's get started, and then we can ask questions later. I want to start as saying, wood is probably one of the oldest structural materials that's been utilized by human civilization. It's kind of a mixed bag because there's something good about it, there's something bad about it. I mean, one big thing you can see that's listed in red, combustible, but with all those things, I think it's a matter of how you engineer and design and account for its strengths and weaknesses. And as of now, at least for in the North American and most of the developed countries, wood is actually very, very popular in low-rise and residential applications. So if you want to build with wood, there's basically 3 options to do it. One is really like old school log cabin. Of course, that's not that old. The really old things, you can find them in some old civilizations like Chinese and Japanese civilizations. Then in the turn of the, not in the turn of century, during the kind of like middle of the last century, 1970s, 1960s-ish, in North America, we figure out a way to mass produce and industrialize and standardize wood products as small 2x4s and wood panels. So that gives rise to what we see now every day, stick framing. It's maybe 90% of the residential market here. Then you got this new stuff that is just coming out in the turn of this new century. In fact, around 2010, that's when this mass timber movement and the movement of tall wood conceptual and also some reality, as you see in this picture, start to take shape around the world. And now it's trickling down now into North America, including Canada and the United States. If you start very old, we can actually learn something from it. Say some people feel like wood buildings, they can't last very long, or you have to paint them every year or every couple of years. I know I have to do that for my house, but some of the amazing things about wood design that wood itself is actually pretty resilient against environmental attack. Like this Japanese temple, it's more than 1,000 years old, and back then there's no chemical preserves, there's no paints. I don't think they paint them. And if you think about tall wood, I mean, that's actually not really new. You see this tower, almost 1,000-year-old in China. It's equivalent to, 18-story building nowadays. So that's tall wood, right? But then the question comes naturally, gee, if tall wood and those resilient wood buildings are so great, why don't we do it? I think at least for the North American and in the US and Canada, everything's driven by the market. Those type of old magnificent wood buildings, they're mostly for religious purposes, or they're palaces, like the Forbidden City. I mean, average homes, you don't have resources to build those type of things. So we are thinking at the turn of century, when industrialization came through, what's the pathway for wood industry? The wood industry basically say, oh, you know what? We're happy with just handling the residential sector, low rise. We got a huge market, so we're happy with it. We'll leave the tall buildings in the cities to concrete and steel. That's what they did. So this market drives the technology. And then we have light frame wood construction, which you can just have some human neighbor to handle everything. You don't need a crane to do those type of things. Nowadays, you probably need some lightweight crane to do the wood trusses, but that's pretty much it, like one day on the job site. Rest of it, you end up using those small pieces, numbers, and then you can actually handle them with a 5 or 6 person crew, and frame up a single family home and frame up a residential home up to maybe 5 or 6 stories. That's the current IBC limit. In current construction of those stick built or 2x4 homes, you don't really see that much glulam composite lumber. Maybe you see them when you want a really open space and a big span. You maybe use them, but those are just too expensive for single family homes. The light frame construction, they have their strengths and weaknesses. One of the most apparent strengths. That's why it's nobody can beat light frame wood in a low-rise residential sector because low cost. I think there's a study can approximate it to frame up a 2-story house. If you take the steel or concrete option, at least in the US, the market price is that it is at least 2 times more expensive than light frame wood. So there's no other option. It is lightweight, which is good, and we see that during not earthquake, like Northridge earthquake, the wood buildings, they get damaged, but they don't collapse that easily. You know, they don't. It's not a life safety issue, and really architectural flexibility. You can frame up a $1 million mansion with wood. You can also do a trailer home with wood. So it's kind of targeted for the residential market, but there's a lot of shortcomings. The first one, which in my personal opinion, is probably one of the most difficult to tackle, is human error. I mean, you think about a light frame wood home, you have to literally do it on site and then nail in maybe 1 million nails with nail guns, but they miss a lot. And there's no good way to systematically check it. Maybe your home inspector from your county coming to the job site. The first time he came in will be the time they pour the foundation. The second time, maybe when they do the roof. He's not going to check every single nail or shear wall. So as a matter of that, it becomes very vulnerable to extreme loading. We see that, like that pictures from a tornado, and we see similar things in hurricanes and earthquakes too. And finally, because you have small wood pieces, it can easily burn, and yeah, once it burns, yeah, it's hard to fight it. So because of that, we have the limitations in building code. Per IBC, it is really not economically viable to do type 1 construction using wood. Type 1, for some of you who are not that familiar, is yeah, typically if you go to type 1, you can build as high as you want. But for light frame wood, it's extremely hard to do because they burn. Currently, if you say, oh, just the wood, how high it can go, it's a type 4 heavy timber, 85 feet. So we because of fire, we pretty much stuck there. And also, I mentioned it is safe, but it is not really resilient. It's a ton of damage. Like this house you see, that's actually a picture from Northridge earthquake. This is a code compliant design because building code prevent building from collapse. It ensures minimal life safety. So you can get out of your home alive, but when you return, yeah, if you don't have earthquake insurance, it's gonna break your back. So those things are actually, as people start to building those stick frame buildings, starting in the 70s and up until 1994 Northridge earthquake. Before that, people just build them. I mean, in fact, we have a separate building code, wood code, which is called IRC, which is International Residential Code. It's coming out of ICC, so it's by the same publisher of IBC. Basically, that one is the prescriptive code. They don't do any calculations on wood buildings. They basically say if you do it this way, then you can build it. It's per code. So it came to Northridge earthquake. Then people realized that their performance is not that good. So the first major project systematically in North American light frame wood is the CUREE Caltech wood frame project. This one lasted quite a while and gathered some data on the existing wood performance. And then we push on to using those data to see what's the best we can do if we incorporate performance-based seismic design. So that's a Northridge, that's a NEESWood project, which funded by National Science Foundation from 2005 and 2009. Then after that, there's a couple of other research projects going on regarding light frame stick-built wood, like the NEESWood. Then there's a study on wind and rain damage due to hurricanes and some other effort. But everything up to 2010 is focused on light frame wood system. So I'm kind of just gonna run through each of them. The CUREE Caltech wood project is a good project. Like I said, the first systematic effort. It's like almost 20 years ago. If you're new to wood research, you want to kind of find the root of why people are doing things on light frame wood the way they did today on research, that's a good place to start. It is funded by FEMA and then, done by a consortium of California universities. Some of the players are very active, like Andre Filiatro and Kelly Cobain. I mean, yeah, people probably know them if you're in wood. The outcome of that is it's the first time people actually systematically tested wood frame system. They go from connections through assembly, which is the wood shear wall, and all the way through shake table test for buildings. I think 2-story or 3. I don't remember, but if you check the website out, they have all the reports available there. I mean, after 20 years, it is still a very interesting read. There is some simplified numerical model framework that was proposed because unlike a steel and concrete structure where you have clearly defined beams and columns, you can do a finite element with a beam element and column element. For wood shear wall, I mean, there's studs, there's sheathing, there's so many nails. How could you do it? So there's a simplified framework that's proposed primarily by Andre Filiatro and Brian Foss in Canada. So there's 2 computer programs. If you still have DOS, you know, they run DOS. There's a Casio that will let you model a wall using connection data and source using wall data to model a building. They also find out the non-structural finishing material really matters. It actually contributes to about 30 to 40% of stiffness and strength in a wood building and other stuff. Then taking that data in 2005, there's a group of people shown here. We're thinking, you know, we know that IBC prevents us from building anything higher than 6 stories. So could we actually just build a 6-story large-scale wood building and make it resilient? Back then, probably resilient is not that much of a word. To get it with a no damage performance during huge earthquakes by applying performance-based seismic design. And then this one's kind of unique because they have an opportunity to test at E-defense, where they can test a 4-story, full-scale 6-story building to validate if their design method works. So I'm gonna try to focus on that one because you know, this is like the result of NEESWood. The researchers call this Capstone test. So basically, it's a 7-story building actually, because they put a 1-story steel moment frame on the bottom for some retail space, and then 6-story wood above. The floor plan is 60 by 40 feet. So this is a test structure. Up to this point, it's still the largest building ever tested on shake table. You know, that's pretty apparent because Japanese shake table is really the world's largest shake table, and they haven't tested anything bigger than this yet. It is done through, the design is done through DDD, which is direct displacement design. The first story steel moment frame, you see all the bracing in them. Their bracings are there because we need to use that steel moment frame as a 3D truss to lift the building. I'll show you later. But during the test, those braces are loosened so that they didn't engage. The construction of building takes about 4 months, and we don't have enough funding to actually occupy the table for 4 months. So the way to do it is to build it in the corner of the lab, as you see, and then after it's all done, then we use 2 overhead cranes to lift the entire building and put it onto the table. So here's the moving footage, time lapse. I think, yeah, if you have been following wood frame research, I'll be surprised if you haven't seen this one. But still, it's quite a thing. You can see the people actually standing on the side to actually balance the building. Yeah. So after the building was put on the table, put on instrumentation, there's a specific instrumentation they use at E-defense because it's an indoor facility where they can do optical tracking. You see all the red LED lights. Then they have high-speed cameras to track the movement. This turned out to be actually a pretty good tool for seismic research and understanding how the building moves. This is, I believe, the last test we did back in 2009. It is 180% of Northridge earthquake original from the Canoga Park recording station. And you see the Japanese table is a 3D table. So you see the vertical motion came first. And then that room you show there is actually the room on the corner where with the lights on. Yeah, you see, I mean, yeah, of course, this inside shot is from the top of the story. You don't expect too much damage, but you probably expect a lot of acceleration, as you can see. The heavily damaged stories are lower. It's actually the second and third story, but I mean, heavily damage is not the one you see in Northridge. It's just some cracking of the drywall over the window openings, which can be easily repaired. So the optical tracking actually really tells us if you design the 6-story building correctly in a larger earthquake. I think that one's probably magnitude 7+. You shouldn't see any like significant wake stories. So the entire building is pretty much like almost like a jello, and then this is the measurement magnified by 20 times. And we also make other measurements, such as the for a multi-story wood building, because of the strong overturning, you do need some tie-down rods going down of your stacked wood shear wall all the way from the top to the bottom, and we measure the tie-down forces, and then we kind of plot it in sync with the building movement, and you can see the entire building is similar to a cantilevered beam out of the ground, and then those tie-down rods are serving as tension fibers. Another another outcome out of the NEESWood project is SAPwood, which is a upgraded software package for doing nonlinear time history analysis of wood buildings. This is still based on the original source framework from the CUREE project, but now we have a nice interface. We can do IDA and automatically multi-record IDA, so everything becomes very easy to use. And if you're interested to do some wood analysis, this is actually a good entry point because it's got a nice user's menu, and then yeah, you can just email me if you have questions. The outcome of the NEESWood project, you have a solid proof that high performance mid-rise wood building is viable through PBSD and light frame wood system. Then direct displacement design becomes kind of a standard or popular for wood design, PBSD. And we have a new tool, and that tool has been validated through numerous large-scale shake table tests. So you can feel a little bit confident using that tool. Then after that, you would think that, okay, you already built the tallest that is allowable by IBC, and then it performs pretty good. Then what else can you do? Oh, it turns out, yeah, you can focus more. That's new construction. But you can actually focus your research on existing problems in existing buildings. And you see on the photo, this is actually, I think that's from the Loma Prieta earthquake. It's the problem of a soft story building, like in California, especially in the Bay Area. People like to have their tuck-in garages on the first story. Intentionally, I mean, maybe not intentionally, creating a weak soft story mechanism. So your upper story can be intact, but your entire building collapse. And then those are existing buildings, so not much you can do about them, but to retrofit them. So NEESWood project is designed to find a methodology to retrofit them and test some real options. So led by the folks over there. And then there's a lot of development going into NEESWood. But again, I'm presenting like the final results, which is shake table validation at UCSD outdoor shake table. They did the construction, then they tested, I believe, 3 or 4, yeah, I think 4 options. One is a cross-laminated timber rocking wall, which we're going to talk about later. Another is steel monoframe, then steel monoframe plus wood shear wall, and then dampers. After they did all those tests and validated their results, they removed all the retrofits. Then they did a collapse test to collapse the building. So this is a collapse test, and I want to make it clear that this is the intentional collapse of the building after all the retrofits are being tested and removed. Because yeah, like one day it's kind of crazy. I look at a YouTube video. They use this test to say, oh, you know, wood is not safe. Then they, you know, show another video of a steel and concrete building. They say, oh yeah, you see, the wood is not safe, but it's not. This is the intentional collapse. Yeah, well, that's probably a student can hold on to laughing. So the NEESWood, so this soft project, yeah, I keep saying NEESWood because I'm involved in that a little bit more. But this soft project outcome, it developed a better understanding of the behavior from how it caused the soft story all the way to collapse. Then it experimentally validated some of the design philosophies, including an early design philosophy, FEMA P695 and also the new one, performance-based seismic retrofit approach proposed by NEESWood team. Some practical options provided, and then there's a new model developed by Dr. Wei-Chang Pan at Clemson. It's called Timber 3D. I believe it runs on MATLAB, and then yeah, if you're interested, you can contact him directly. But this model, it is more involved than the SAP. Basically, everything is 12-degree freedom, and you need to do a lot of things. But the real catch here is to try to capture collapse. I think he did a pretty decent job there. Then, you know, following that project, really, I mean, some of the techniques were applied in real-life retrofits of San Francisco City. They have a mandate on the retrofit. So if now, you know, if you take a look at light frame or stick build wood system, this is the best you can do by 2010. You can do up to 6 stories. They can be low damage to seismic. You have to do PBSD, but it doesn't really address some of the fundamental weaknesses I outlined earlier. The individual members and connections are still weak. The fire, you know, there's no way around that. Then again, human error, like this building is built in a Japanese lab by a whole bunch of Japanese carpenters. I mean, it's not the same quality control you can have in a construction site. So, well, then we need to think of something new. The simple idea is, how about we use a lot of wood? How about we use just solid wood? In fact, the Germans and I believe Austrians, they think of this first. They are saying, why don't we just start producing glue lamp panels? We just use small members and we just glue them together to cause panels. Then we can build building out of it. There's a misconception that, oh, a tall building has to be all CLT. I mean, in fact, we call it not a CLT building, we call it a mass timber building. Mass timber building is a combination of CLT and big glue lamp, column and beam members. But in this example you see in the picture, that's a London building, which is already completed a couple of years ago. That one is all CLT panels. So how come this mass timber or CLT becomes a game changer? Because it addressed the three limitations of light-frame wood. The first one is human error. Every single panel, I mean, if you buy them, they have to produce in factory. And then if you have detailed designs, then they'll actually cut it with the computer CNC machines in factory and wrap it up and then put it on site. Then all you need to do is just install them with some, not by a million small nails, but by some specially designed connectors that are easy to inspect. Like you see the construction process here. It is easy to detect if the workers install those brackets incorrectly or not. In fact, an inspector can just walk in like one story every day and then get it done. It is a stronger material if you think about the connections on the right. You know, not all the CLT connection has to be as bulky as that, but at least you have the option. In fact, we just did some testing of CLT rocking walls. The steel will yield before you can damage the wood. Then finally, the fire resistance. For wood, counterintuitively, it is actually the best structural material under high temperature. Because the steel and the rebars within concrete, their property changes under high temperature. And this is a photo from the 1906 San Francisco earthquake, where fire after earthquake, they burned down a building. It is an enclosed fire situation, so the temperature inside gets really high. You can see the steel beam melted, but they were supported by a timber beam, and that beam 1906. So there's no special treatment for that beam. It's just survives because of the volume. Now back to 2015, AWC, American Wood Council, did a fire test of CLT compartment. This is called a burnout test, which is saying, considering the worst situation, your sprinkler failed, the fire people can't get in because of earthquake, then the fire has to burn everything inside the unit and then self-extinguish. So they let it on with a whole bunch of furniture. Yeah, this is probably more furniture than you would typically put in such a tight space. After an hour, everything burned down. You know, there's no couches, there's no TV. Then they remove the debris, then remove the drywall. The wood is pretty much intact, but you could say, okay, well, I mean, that's just say it's because of the drywall. True, but if you imagine what is the temperature inside that for burning for an hour, if you have other type of floor diaphragm or floor beam system, you probably have some permanent deformation afterwards, but not with wood. So if you combine all the factors here, it is actually a new way to build a tall building in almost 100 years, because the first metal building over 10-story is down in Chicago, 1884. Gee, that's more than 100 years ago. The first reinforced concrete building is in Cincinnati, 1903. After 100 years, you can only build 10-story and plus building with those two materials. Finally, in 2012 in Melbourne, Australia, they did a 10-story with CLT. But you say, okay, well, hold on. I mean, that's all good, but do we have enough trees for it? You're going to cut down all the trees to build your buildings? There's something called the sustainable forest management. Yeah, if you just have a forest and you chop it down without doing anything, it'll be bad. But those are the pictures from New Zealand. I mean, if you farm forests just like you farm a crop, it's a longer cycle, maybe 15 to 20-year cycle, but they have successfully done that in New Zealand. In fact, I believe for New Zealand, I mean, you think about it's not that much land, but timber export is one of their major economic drive. Even Japan, they export timber to China. And I remember, like when we were in New Zealand for a World Conference on Timber Engineering, I think one of their very high government officials were coming here just because how important this forestry is to them. So it can be done. And then an analogy I always want to make is chickens. I mean, you have to think about wood as a renewable resource, which it is. it can grow again. So it's like chicken. If you eat more chicken, you know, the chicken population will grow. If you use more wood in a sustainable way, we're gonna probably have more forest. Yeah, if you make it a really prime material to use everywhere and people can make money out of it, they probably invest to try to turn Nevada into forest. Some of the existing wood buildings, this one, the one I showed you earlier on, that's in London. What's amazing about it, it takes 4 carpenters 27 days to complete the structural framing. Yeah, of course, to finish the building, it takes a little bit close to a year, but the framing itself, if you compare that with live frame, that's not imaginable. It's four people. Actually, that includes a crane operator. This one is a mass timber building designed by Michael Green in Canada. I want to mention this one because it's a perfect example of what I'm talking about. It's not purely CLT. It's a glulam, column, beam plus CLT, which you can see provide you with great open space. Then you have the current world record holder in height. It's Brooks Commons student dorm in UBC, 18-story. But this one, they actually use the concrete elevator core as the lateral system. Because right now, there's actually no code accepted lateral wood solutions, you know, for CLT. But this is just because of the the code cycle is so slow. If you want to really do it, you can do it through special permission. Carbon 12 in Portland, it's a residential building. I think they're starting selling it now. And this one, the lateral system, is a braced steel frame. So in fact, like my opinion is that if you want to do a mass timber tallwood building now, it's actually not a bad idea to use some existing code approved lateral system with steel and concrete. The framework project is really the first one that aspires to use only wood. This one used the post-tension rocking wall system, but they actually went through a lot of paperwork and testing to convince the building officials that it is viable. Then there's some, like, yeah, you don't always have to build over 10 stories. Like here in my neck of the wood in Denver, they're doing a 5-story commercial. The investor likes it because, you know, he just likes wood buildings. There's more to come in different sizes and shapes. You probably see them in news before. I know them. But now let's get back to Seismic. Okay, this new heavy timber, mass timber, whatever you see it, it's great. It has potentials because it handles the fire situation. What have people done with it on Seismic? After it is invented, in fact, in Europe, people started doing some testing like walls, like small sheet table tests in Macedonia and Slovenia. Then in Italy, I mean, that's probably the only European country that are kind of actually care about earthquake. They did a project in Japan. They tested a 7-story tower. Then there's in Canada, they're doing some testing, and then in the US too, in Japan even. Like I was just going back from Tokyo, like two weeks ago. They are testing CLT platform construction in Japan. They're trying to sell houses, but all those are what we call a platform construction. Platform construction is where the wall was stopped by the diaphragm. So you do a wall, then you put a diaphragm on, that becomes a platform. You do another wall. That's a traditional way to do it. But there's new ways if you want to see some low damage in earthquakes, because platform system, as revealed by the Japanese test and the Italian test, they'll have some pretty hard to fix damage at the corner because of overturning. But in New Zealand, as people started thinking about combining pre-stressing with mass timber. And then we kind of pick up from that idea, say, let's do tallwood with that. We actually started to doing that. I'll talk about that. But before we do that, I mean, basics for engineers, what matters is the code. If you don't get your design approved by the code, it doesn't really mean anything. So there's an effort to actually put CLT shear walls into the code. through the FEMA P695 project. If you don't know what that is basically, if you want to go into that table, R factor in SE7, you need to go through this for any new system. This project is led by John Vanderlinde at Colorado State University. It's funded by USDA. It's still going on, but I think they're almost there. They're almost there. I think you will probably see an R factor for CLT shear wall later this year, later next year, 2018. Then back to the resilient part. Now it's NSF, right? So TallWood is NEES. That's actually an opportunity to actually do it right for the first time. Because yeah, we don't want to run into the old problem have that with light frame wood construction. Right now, after all the existing buildings built, we find out we have a soft story. We don't want to do that, so we want to really do something really above code, which is resilient. But we need to do some preparation work. We need to first figure out if everybody really wants this to build consensus. Secondly, we need to test some components that can actually get us there. So that's the purpose of the NEES planning project. If you remember, between NEES and the NHERI, there's a 1-year period where they give a planning grant. This is one of them. To build consensus, we have the first US TallWood workshop in 2015 in Seattle. Then you see the people in the picture. I mean, I would say only like 10% of them are academias. Others are building officials, design engineers, architects, wood industry. So we're building consensus saying, should we go with this route? We actually end up deciding to do a tiered approach because the industry really want to see tier 1, just meet the build code minimum, do an equivalent design and move forward. But then there's a tier 3, like shoot for the sky. We're trying to do a resiliency-based design. We'll design for downtime, as you see here. Then the second part of the NEES planning grant, we did a test of component of the post-tension rocking wall at the University of Washington State University. What I find out is that, yeah, this guy is doing great in terms of ductility. If you look at the hysteresis here, just look at the backbone. This is like a perfect elastoplastic behavior, and then it can hold the strength up to almost 10% drift. And then the only damage you see is at the toe of the CLT panel. So if you examine the initial data provided by this planning grant, we have a mass timber system, can be as ductile as current steel and concrete system, and maintains no damage. And it's only 1/5 the weight of concrete. Yeah, you can reduce your seismic demand by almost 80%. I mean, yeah, just for structural part. So do we dare to ask for above code seismic performance? Yeah, sure, and we should do it. So we use this argument to write another proposal to NSF. Then 2016 we get funded to do NEERI TallWood Project, which is like Jim mentioned earlier. 6 university collaboration with a lot of industry buy-in and international collaboration. Like Andy Buchanan, it's like the godfather of timber research in New Zealand, and then Marian Popovsky representing the Canadian side. There's a website that you can check on that, but the game plan is basically this. First, we're gonna work with architects to figure out if you're gonna do TallWood buildings, what kind of floor plan can sell. Yeah. It doesn't really make sense for us to come up with some floor plan within closed door, and then the investor don't want to invest on it. So we collaborated with Lever Architects, and they are actually providing archetypes designs. So we're going to review them actually later today. Then we do investigative testing at the system level, including 2 tests. One is at UCSD. It's a 2-story conceptual test with CLT diaphragms and rocking walls. Full-scale shake table test we just completed, and then coming this next year, we're doing component assembly test at LEHIGH, which I'm going to talk about a little bit later, and to load those walls in biaxial motion and also incorporate long structural systems. After we gather the data from those investigative testing, we're going to do R&D and finally come up with a 10-story design concept, and then build it and test it, validate our results in 2020. Like I mentioned, the full-scale two-story test was just done in San Diego. I'm going to show you a footage here. It's a Northridge ×2. Basically, what it means is that to show how resilient it is, we run Northridge earthquake one after another without stopping. So yeah, that's the first Northridge earthquake. The second one. So after that, we actually did a total of 14 earthquakes. There's like 5 MCE level, one that's actually exceeding MCE. We reached the maximum building drift of 5%, but it's there's not that much damage. I mean, after that, we actually take out the wall and then look at the toe. I mean, that's the damage you see, and then there's some chipping, but the gravity frame and everything remains damage free. We did yield a few rebars. We know that thanks for the low sales provided by LEHIGH Lab. And then yeah, that's it. Then moving forward, next year, I think early next year, we're gonna do at LEHIGH a biaxial loading test to study in a closer detail on the rocking wall behavior under biaxial loading, and also the joints connections, because I mean USSD table, nice as it is 1D table. That's what we're gonna do next year early. Then the second phase of LEHIGH test, we're gonna actually include the non-structural components, because if you're talking about the design for resiliency and downtime, non-structural components, the damage to those are actually a driving factor. So we want to try some new designs that will remain damage-free or very quickly repairable damage after large lateral drifts. This was led by CUREE from University of Reno, Nevada, Reno. And yeah, don't forget, we're doing a 10-story building in 2020. I don't know if you're industry or if you're a researcher. If you're a researcher, if you want to do a payload test or invest in some system or non-structural even, yeah, email me and talk to Joy and try to throw a proposal in maybe next year. And if you're industry, want to test some of your items in the 10-story building, this is like once in a lifetime opportunity to do that. Really show to your customers that your product will survive. So the conclusions, I mean, because this is the overview, I don't really have any specific conclusions. The first one, you can use wood to build buildings. Yeah, you say, okay, well, that's inspiring. Yeah, but I mean tall ones. Yeah, over 10 story. The wood building has the potential to be very resilient against the large multiple hazard. Yeah, we're just talking about seismic here, but in fact, you think about wind and CLT, you can do a lot of things here, but it has to be done right. And there are still a lot we don't know about wood buildings, especially when tall wood buildings are totally a new animal. More research is needed. Seismic, what I covered here, is just a small part of it. So to conclude, this is really a very exciting time for wood engineering. And you may ask what will happen next. Yep, I think that's actually part of why I was in this profession at first. I mean, do research is to explore for what you don't know. Final acknowledgement to NSF with the funding to do to pursue this tall wood topic, and then our wonderful industry supporters listed here, and thanks for LEHIGH and my collaborator, and the opportunity for this for this chance to talk with you all guys. And yeah, we're actively seeking research industry partners. Contact us if you're interested. With that, I'd like to thank you and take some questions. And this slide has a lot of information. If you just go to the website, yeah, as it's shown here, I will keep updating everything. You'll be informed. Thanks.
All right, great. Thanks, Charlene. So we could open up the forum to anyone that wants to ask questions. At this point, you can either type it in the chat or unmute yourself and ask. So right now, the forum is open to anybody for questions.
Yeah, Shailene, this is Jim. I have a question for you. You had a slide that said that there's potentially an 80% reduction in the seismic loading comparing wood timber with concrete. Is that just based on the weight of the material? Because you have to satisfy strength and stiffness. And
yeah, I mean, yeah, that's right. That's probably. I mean, yeah, that's just the weight of the structure itself. So basically, you have a reduction of 80% of your structural weight. But again, you have to satisfy like those things, and then you have to have other systems and non-structured systems. So I would say realistically, for a wood building versus a concrete building, your weight reduction is probably close to maybe 30%. I mean, it's not gonna be 80. But it depends on what kind of system you use. If you're using an open floor plan system like what we tested, the reduction will be less. But if you're going for the London building and the 40 building in Melbourne, which is all CLT panels, your reduction will be more because platform CLT is actually very, very stiff. Yeah, I think you make a great point. Yeah, it's probably should not be 80%. That's just a simple comparison of the density of the material.
Yeah. Okay. Thanks.
All right. If there are any more questions, you could feel free to unmute yourself. We'll give just another minute or two for the forum.
Yeah. In fact, I think the Melbourne building they did the 30 option because they can save on foundation cost because of the total weight. That's became a driving factor for that build.
Yeah, maybe while we're waiting, if there's any other questions, this is Jim Ripples again. I could just note to the audience here, if you haven't become aware of it, there's another seminar tomorrow, same seminar series by Professor Simon Laflamme from Iowa State University, and he'll be talking about high performance control systems for multi-hazard mitigation. So if you're interested, I would encourage you to go to DesignSafe and register, and then you could also, of course, get additional information through the abstract and the registration information.
Yeah, here's a question on Sapwood program. Just email me. I think, yeah, originally it can be downloaded from the NEES hub. But yeah, now NEES hub has been transferred to DesignSafe, and then I don't know the link, but if you just email me, I'll get my emails up here. If you just email me, I can just send it to you. It's you don't need to install it. It's just a zip file. I give it to you. You got all the users menu, examples, and everything. Then you can study yourself. Yeah, but eventually it's gonna be on DesignSafe. But I think you just need to kind of categorize it a little bit.
Are there any other questions for the speaker? Shailing, I think everyone has your email address, or they can easily find your email address, I think, just by going to your institution.
Yeah, that's right.
I was going to suggest, that perhaps they may want to contact you for some collaborative discussions, or maybe they have some additional questions they're not coming to mind at this point, so they can contact you, I think, in the future there. So I was going to suggest if there's not any other questions or need for discussion, we can go ahead and complete the seminar. And wanted to thank you, Shailene, for an excellent seminar, and I think it was well received, and we appreciate you volunteering to do this.
Yeah, thank you, Jim, for the opportunity. And yeah, I think we're dead on time.
Yeah, so the only other thing I wanted to mention, and Shailene, you and I guess, started to collaborate because of this. We have researcher seminars, or workshops, should I say, in which the NEERI facilities will showcase their capabilities and give researchers ideas and opportunities to prepare research proposals and then be successful in conducting research. So I wanted to mention, in fact, we're having one December 4th, and if you're interested, you can go to Design Safe and find information and register for that. And there are participant travel funds available, so I'd encourage you, if you want to do so, to do that rather quickly, since the workshop is less than a week away there. And Shailene, you've been to these a few times, and
Yeah.
I think that you've been.
Yeah, I think it's really helpful. I think yeah, before we actually get this grant, you do need to do some prep work, especially if you're gonna propose testing at LEHIGH. You need to go to those seminars, and it's really, it'll enrich your proposals. And then of course it's always good that you're well prepared to actually do it.
Yeah. Okay. Well, I guess with that, Shailene, again, thank you again very much.
Yep.
We'll be in touch, and appreciate everyone else participating, and stay tuned. As I said, there's future seminars, including one tomorrow. And with that, I'll go ahead and log out here. Okay,
Thank you, Jimmy. Yeah, nice to see everybody. Thank you. Bye.